Welcome to the second part of the first lecture on Introduction to Communication Engineering. In this lecture, we will talk about channel impairments or some of the issues or problems that the signals might face while propagating through the channel. These are some common phenomena that happen: attenuation, distortion, noise, and multi-user interference. We will talk about them one by one. First of all, to give a general overview of this, these are all problematic for the signals and degrades the quality of a signal. And the amount of these impairments actually depend on the type of the channel. So first of all, let's talk about attenuation. It's very obvious that if you transmit a signal through a channel, it will lose its power as it travels forward, right? That is what attenuation is. Here you can see an illustration of it. We start off with a fairly high value of amplitude, and then as the signal passes through the channel, value of the amplitude decreases. This is what attenuation is. Signal attenuation or degradation exists in all media. If you use a wired medium, let's say telephone channel, you will experience attenuation there. There are multiple ways that we can cope up with this problem. We will discuss about these issues later on in the course, but for the time being, we will learn that this attenuation happens for all the medium. If you use wired medium like telephone channel, attenuation takes place. If you use wireless medium like mobile phone, attenuation also takes place there. But wireless medium has more attenuation than wired channel. And obviously the attenuation increases with the distance, and the optical fiber has least attenuation of all the mediums. Another problem we encounter is distortion. When a signal passes through a channel, the signal gets distorted. It doesn't matter if the channel is passing through a wire, optical fiber or wireless medium, distortion takes place. In the case of wireless medium, due to multipath propagation, time-dependent randomness of particles, and also due to different attenuation of different frequency components of a signal, wireless medium experiences highest distortion. Due to distortion, inter-symbol interference happens. So here is an illustration. You can see that we started off with a signal which is a digital sequence 1, 1, 0 and 1. Then it gets distorted. You see that shape of the 1 is not as rectangular as it is in the transmitting end. We have received the 1, but it is a very distorted version of 1. This 1 is also distorted. 0 is 0, so there is nothing to be distorted here, and 1 is also distorted. The problem here is, you can see that this symbol 1 and this symbol 1 are experiencing some interference. This one is interfered by the response of this one here. This is not a problem if the sequence is 1, 1, but let's say in this case, in this time frame, in this t time frame, we are expected to get a 0 value. But due to the inter-symbol interference, we can see that some portion of this sequence 1, actually we are receiving it in this time frame. Also some portion of this symbol we are receiving in this time frame. So when we are reconstructing the sequence from the received signal, we actually do it by setting a threshold. Let's say this is my threshold value. So then it's okay that if we are getting some value over the threshold, we will consider it 1. As we can see that in this time frame the value is over this threshold, so we will consider it 1. And in this time frame the value is less than the threshold, we will consider it 0. Let's say our threshold value is this. Then in the case of 1, we are getting values over the threshold, so it is 1. But in the case of 0, we are also getting the value over 1, so the reconstructor might consider it as a 1. So we need to choose this threshold carefully, and if the distortion is very high, a very high threshold may also detect this 0 as 1 due to high level of distortion. The next channel impairment we are going to talk about is noise. This problem does not require a lot of introduction. We all regularly face this problem while communicating via mobile phone or telephone. Here is an example of noise, a very random signal, no pattern in it, and this is a particular signal buried in noise. You can see the black lines, that is the original signal values, that is actually transmitted signal, but when we are receiving it in the receiving end, we will get the red signal, which is actually the original signal buried in noise. There are two types of noise: channel noise or external noise. These are the noise that signal gets mixed with while propagating through the channel, automobile ignition radiation, microwave oven, lightning, etc. Very random and obviously undesirable. Then another type of noise is receiver background noise or internal noise. It is actually the thermal noise and radiation emission from the electronic devices. So the difference is external noise is easy to remove. If we use proper design, then it can be removed easily, but internal noise is a big problem. It is actually a tough thing to handle. The final impairment we are dealing with is interference. Interference is also unwanted signal like noise, but the difference is interference is more structured. Let me give you an example. Whenever we are making a telephone call, sometimes we may overhear some other people we are not talking. That is the signal of someone else. That is what an example of interference. There are several types of interferences, such as electromagnetic interference, co-channel interference, adjacent channel interference, and intercarrier interference. About the interferences like co-channel interference, adjacent channel interference, this interference will be discussed more in some of the future courses like wireless communication. For the time being, it is enough for us to know that interference are more structured than noise. And then comes electromagnetic spectrum. We are actually familiar with this spectrum from a very early age. Low frequency signals such as radio signal have high wavelength, and as the wavelength decreases, frequency increases, and gamma ray has the highest frequency, and visible light is actually a small portion of this electromagnetic spectrum. Okay, now new topic, signal bandwidth. What is bandwidth? Bandwidth is the measure of frequency contents of a signal. Let's say there is an example. Let's say this is a time domain signal. Here x-axis is time and y-axis is amplitude value. If we want to analyze this signal in frequency domain, we have to take the Fourier transform of it. This is the frequency representation of the signal. Here you can see that the signal has frequency components from 0 Hz up to 4000 Hz. So assuming from the frequency spectrum, we can conclude that this is a human speech, because the bandwidth of the human speech is actually roughly 4 kHz. So how we can measure the bandwidth of a signal? Actually, we measure the bandwidth of a signal from different perspectives, but the most common thing is we actually measure the bandwidth from the frequency representation of the signal. Let's say this is the Fourier transform or the frequency representation of a signal. So the one way to define bandwidth is the absolute bandwidth. Absolute bandwidth is all the frequencies that are available in a signal. So in this spectrum, you can see that frequency is available all the way up to this value, which is actually B. The total frequency range is 2B, so the bandwidth is actually B. The next way of measuring bandwidth is 3 dB bandwidth or half power bandwidth. As you can see in this illustration, this is a frequency spectrum of a signal. The majority portion of the spectrum is close to the zero frequency, and as the frequency increases, the components corresponding to those frequencies also decrease. So if we want to consider total power in the positive frequency side, we have to go up to this frequency. So this frequency component covers the total power of the signal. Any frequency less than this will not cover total power. So there is a certain frequency somewhere in between this region where the power covered by that frequency is half of total power. That frequency is called 3 dB bandwidth. Here you can see that where the dashed line has cut the x-axis is the 3 dB frequency or 3 dB bandwidth. From the formula to calculate bandwidth, it can be shown that if the amplitude at zero frequency is A, then the frequency where the amplitude is actually A by root 2 is the 3 dB bandwidth frequency. In other words, if we normalize it, then the amplitude of the frequency component at zero frequency is 1, then amplitude of the component at 3 dB frequency is actually 1 by root 2. The next way of calculating bandwidth is equivalent noise bandwidth. Before explaining the formula and the definition, let's show me a formula how you can calculate the power of a frequency spectrum. Let's say in this figure, let's say consider the black spectrum, not the blue one, the black one. If we want to calculate the total power of that frequency spectrum in the positive side, what we need to do is we have to take the square of the modulus of the spectrum, HF modulus square. HF is the frequency spectrum values. We have to take the square of the modulus of it and then integrate it from 0 to infinity. So let's say if we want to calculate the power of this frequency spectrum here, what we will do is we have to determine the function of this frequency spectrum, that is HF. Then we have to take the square of the modulus of it and then integrate it from 0 to infinity. Now we can see that in this spectrum there is no frequency component after B hertz or B frequency. So instead of taking the integration up to infinity, we can just set the upper limit to B. That is how we can calculate the power of a frequency spectrum. Now what is equivalent noise bandwidth? Equivalent noise bandwidth is the width of a fictitious rectangular spectrum such that the power in that rectangular band is equal to the power associated with the actual spectrum over the positive frequency. In a very easy way, we have to draw a rectangular spectrum here whose height is equal to the height of the original spectrum at 0 hertz. You can see that the height of this blue rectangular spectrum is equal to the height of the black spectrum at 0 hertz, and it is a rectangular spectrum. So if we have decided what the height of a rectangle is, then we just need to define what the width of it will be. Now this width is actually the bandwidth value. How we can set it? It is very easy. At first we have to understand the definition. The definition is, let's say this black spectrum here covers a power which is equal to P in the positive direction. Let's say from 0 to this value it has a power P. Now we have to draw another spectrum which is actually blue spectrum, a rectangular spectrum, that will also cover the same power P. Now as you can see, it is a rectangular spectrum, so it will obviously do not need to go up to this point to cover the power. So it will be somewhere in from here to here. How we can determine it, where the width will be? As we know the formula for calculating the power, we can just calculate the power of the positive side by integrating the square of the spectrum from 0 to infinity. That is the power of this black spectrum. Now the definition is the power of this blue portion will need to be same. So what is the power of this blue portion? Now again we have to integrate it from 0 to some value, and the integration will be over h of 0 square, right? Now as it is a rectangular spectrum, the integration is quite straightforward. We will just get the multiplication of this value multiplied by this bandwidth. So as we know this value, now we can, to get the equivalent bandwidth, we just need to divide the total power by this square of this amplitude.
The next way of calculating bandwidth is zero crossing bandwidth or nocturnal bandwidth. Here you can see a frequency spectrum. In the positive direction, it touches the zero amplitude line in frequency axis multiple times, and in the negative frequency line it also does the same. So the first time the frequency spectrum attains at zero amplitude is in this frequency. Let's say we call it F2 frequency, and in the negative side, the first time the spectrum touches zero amplitude is at this frequency. Let's say we call it F1 frequency. Then the total bandwidth in this region is F2 minus F1. This is actually the double of the null bandwidth, so it is denoted as 2Bn. Bn means null bandwidth. So the null bandwidth is actually the difference between this value minus this value divided by 2. If it is symmetric, then calculating from zero frequency to the first cut is enough to determine the nocturnal bandwidth. Then comes X% power bandwidth. It is actually similar to the half power bandwidth. Previously we have talked about half power bandwidth. In half power bandwidth, we calculated the frequency which covers the half of total power. In this case, this was the frequency which covers the half of total power of the spectrum. In the case of X% power bandwidth, you will given a certain percentage of power to cover. Let's say you have asked to determine 80% bandwidth. In that case, if this was the spectrum, then you have to determine which frequency covers 80% of total power. How we can do that? As you have learned already, we can calculate the total power of a spectrum using this formula, right? You have to determine the total power first, then you have to calculate the 80% total power. Then again, you have to carry out the same calculation, but this time you have to set the upper limit as an unknown frequency, and that unknown frequency is actually your 80% power bandwidth. Then you have to carry out the calculation and finally find the upper limit, which is the answer for 80% power bandwidth. This will be more clear if I illustrate this with a problem. So this is an example problem which will help you understand the concepts of bandwidth and X% power bandwidth better. This problem states that determine 60% bandwidth of the following spectrum. This is the frequency spectrum. It shows that the frequency components are spread up to 500 Hz in the positive frequency, and the negative part it is also spread up to minus 500 Hz, and the amplitude at 0 frequency is 10. So we have to determine the 60% bandwidth of this spectrum. So the first step is you have to calculate the total power. How can you do that? The first step is you have to determine the equation of the spectrum, that is HF. So we always calculate the power of the positive half. So don't worry about the negative portion, just determine the equation of the positive part. So in the positive part, it is a straight line actually. You can determine its slope and the cut of y-axis, and finally you get the equation, which is HF equal to 10 minus 0.02 F. If you have determined what is HF, then you need to calculate the total power. The equation for that is the integration of this HF square, and the limit will be 0 to infinity. But as you can see in this spectrum, no frequency component lies beyond 500 Hz. So setting the limit to 500 is enough. Carrying out this calculation by either calculator or by hands, whatever you do, you will get this result. 50,000 by 3 is the total power. It is in watts. Now you are asked to determine 60% power bandwidth. So the first task is to calculate 60% of total power. That is this into 0.6, which is 10,000. Then again we have to calculate this same equation. You can see that this is same thing. The difference is now we are setting the upper limit to an unknown value b. This b is our answer. This b is the 60% bandwidth. Okay, and the result will be 10,000. Why is that? Because this thing in the integration actually gives you a measurement of power, and this limit tells you what percentage of a power you are getting. If you set the limit from 0 to infinity, you are getting the total power. If you set b equal to 20 Hz, then this equation will give you the power between 0 to 20 Hz. Now, as we don't know the 60% bandwidth, we are choosing this an unknown value b, and this calculation result will be equal to 10,000. Again, you have to carry out this calculation by hand, and this equation will turn out something like this. Then solving for this quadratic equation, you will get 3 answers, because the order of the equation is 3, but only one of the solution is actually real number. The rest are complex conjugates, so that those are out of equation. So your answer is 131.59685 Hz. What does that mean? That means is if you carry out this integration from 0 to 131.59685 Hz, you will actually get the 60% of the total power of the spectrum.